In this video, I'll be talking about Lab 5, where we looked at a falling magnet. The purpose of this lab is to use a computational model to calculate the theoretical time it takes for a bar magnet to fall through an aluminum tube, and then to compare this prediction to data we take experimentally. Through the experiment, we found the time the magnet took to fall through the aluminum tube to be 1.56 seconds. The computational model, on the other hand, gave us a value of 2.478 seconds. Here are the physical principles we used in this experiment. So we used the dipole magnetic field equation shown there. We also use Faraday's law and a special use of Faraday's law from video 43. We then use the magnetic force equation, F equals I delta L cross B, and then we use the force on loop equation, which is derived from that equation, F equals I times 2 pi r times B sine theta, and we also use Newton's second. The dipole magnetic field equation was used to calculate the magnetic field of the bar magnet. Then d flux dt was calculated using the equation derived from video 43. Finally, the magnetic force was calculated using the force on loop equation on the previous slide. And then we used Newton's second law to update the velocity and position of the bar magnet over time. For our experiment, we used the magnetometer app that we use in experiment 3, and we first determined which side of the magnet was the North Pole. We then took 5 recordings of the magnet being dropped through a tube of aluminum foil, and from the videos, the time it took for the magnet to pass through the tube was found for each of the 5 runs. The average time was calculated. So in the experiment, the system is the bar magnet and the surroundings is everything else. And the average time we got was 1.56 seconds. Here are the initial conditions for our code. So the dimensions of the foil tube, the length was 0.27 meters, the width was 0.008 meters, the inner radius was 0.015 meters, and the total radius is the width plus the inner radius. And for the bar magnet, the mass was 0.23 kilograms, and the dipole moment was 2.29, and this was from Lab 3. So this code worked by first setting the initial conditions described previously. The magnetic field produced by the bar magnet was then calculated using the dipole equation. Then d flux dt, which is the change of flux over the change in time, was calculated for each ring of the tube due to the falling magnet. A while loop was then used to calculate the magnetic force on the bar magnet from the tube, the current in each ring, the magnetic field at each ring, and the magnetic force and net force on the magnet. Finally, a plot was created to visualize the model. Here's the output of the code. The time we got from the code is 2.478 seconds. So this doesn't match our experimental time. Some sources of error could be the code did not take into consideration air resistance or any other forces other than the magnetic force and gravity, and the dipole moment for the bar magnet could be incorrect. Here are the interpreting the simulation questions. So for the colors of the currents, the red current is counterclockwise and the blue is clockwise. And this can be determined using Lenz's law, which states that the induced current in the magnet will create a B field that opposes the change in B field as the magnet is falling. If you flip the magnet around, the induced current will occur in the opposite direction, but it will take the same time and visually it will look the same. The experimental time was 1.56 seconds and the computed time from the model is 2.48 seconds. So the computational model could be made more accurate by using more rings in its calculation and by ensuring that the magnet's dipole moment is accurate. The places in the velocity versus time graph where the slope is 0 tell us when there is 0 net force on the system, the bar magnet. The places where the slope is negative tell us when the force of gravity outweighs the magnetic force and the magnet is falling downwards. What if the resistivity of the conductor was reduced to close to 0? If resistivity were to decrease based on Ohm's law, the current induced would increase. So I equals mth over R. If R were to decrease, I would increase. This could lead to the resultant magnetic force counteracting gravity and possibly preventing the magnet from falling. What if holes or slots were cut into the tube? The current would be disrupted, which would lead to less current overall. Due to the decreased current, the magnetic force would also be reduced, and so the magnet would fall through the tube quicker.